Hi, good afternoon. I hope you don't fall asleep during my presentation after such a hefty lunch. Hopefully I'm not going to make it worse by showing to you too much science behind machine learning, but I'm going to talk to you about building a recommender system using Apache Spark and integrated using Akka. A while back I started working on KnowNow, a knowledge management system. And one of the things I worked on was recommending knowledge to people. And as part of that, I experimented a little bit with Apache Spark and found out how to use it. And I thought it would be a good story to tell you and show you what goes into building a recommender system and using it in your application. So it's going to be a bit of a practical session instead of talking too much formulas, cost functions, and all that sort of stuff. If you're into that, I suggest you watch one of the other Spark sessions that's going on during the conference. I need your ratings, so if you like this session, rate it, otherwise, no. Just tell me what you like and didn't like, and hopefully it will be a good session for you. So who am I? I'm a technical evangelist for info support. This is sort of the commercial talk for me, and it stops right here. I'm just very, very happy to do machine learning. I love working on smart systems that help you beyond just showing data to the user. I love systems that sort of help you along the way. For example, recommendations for knowledge, obviously, but also, is this a smart thing to buy now, or is it something that I would buy later? Train the computer to help you make smarter decisions. That's what I like. It's also kind of weird. Scala days, normal Microsoft MVP. Apparently you can be these days if you do Scala. So if you look at the internet, and if I browse the internet, and especially Netflix and Spotify and stuff like that, I was wondering, that's interesting. There's a lot of movies, 35,000 movies on Netflix. That's a whole lot of stuff. And of course you can search, that's all right. But what do you find? The things you know, that's what you find. That's going to be a problem. Google invented a search engine. If you ask me, there were search engines before, but okay, they made it smarter. But there's a limit to it. You only find what you were looking for. If you know what to search, then Google can help you. A search engine is a perfect place. But if you look at the case for Netflix and Spotify, then there's a small problem. There could be music in there that I really, really like, but I don't know the title of the album or the title of the song, so I'm never going to see it. Same goes for a movie. I know I like the Avengers, but there could be another movie that is very similar to the Avengers, but I've never heard of it, so how am I going to find it? I won't, because I don't know how it's called. I don't know where to find it, what the keywords are, and hopefully someone tagged the movies so I can search for a category and then we'll get to the alternative to Avengers. But yeah, it's kind of, so how do these companies solve this problem? Well, they start to recommend stuff to you. They start to learn from you as a user what you like. So if you're watching the movie Avengers, the system will record that you like the Avengers and that the Avengers is an action movie. It's about superheroes. It's about action, maybe shooting, all sorts of stuff. And the next thing they do is they try to profile what you are for kind of person. And they're going to recommend you movies that are very similar based on some common properties of the movie. So that's what recommender systems are in essence. They're just a piece of software that profiles you, that knows what you like and what you didn't like, and then tries to find other stuff based on those properties that you like and recommend it to you. And there are many, many ways to do it. These are just 3 of those methods. Matchbox recommendations is one of them. I'm not going to explain them all today. And these are just a few ideas. And I'm going to show you the alternating least squares algorithm, which is implemented by Apache Spark. Surprise, surprise. Why would you do that? Because the other ones are not implemented in Apache Spark. The idea is that no matter what you choose, they're all going to be wrong. And you were thinking, he's going to say there's one that's the best. There isn't, because you don't know what the user likes and doesn't like. Machine learning is this art of approximation, I'd like to call. In Dutch, we would say, it is de kunst van ongeveer. It doesn't sound anything like approximation, but what we're going to do is we're going to get as close as possible to what the user likes. So you're never going to reach 100%. And if you think about it, if you don't want to reach 100%, then why would you invest a lot of time in researching all these algorithms? And these are just 3, and there are a lot of other algorithms that you can use. Here's one tip I would like to give you before we start talking about code and doing other things. If at some point you want recommendations in your system, you think the user needs help finding new stuff, basically, then choose whatever you like. Choose a product that you're familiar with, such as Apache Spark. There are others, Mahout, Hadoop. There's even a Microsoft product, Azure ML. Actually, don't use that. It's very expensive. No matter what you do, pick a tool that you like, pick a tool that you know, and use that. Don't worry about these algorithms. And we're going to talk about one algorithm, but don't worry, it will be all right. Any people that use Spark today? Less than I hoped for. No. Okay. So Apache Spark is a tool that allows you to build distributed programs that work on a set of data and can calculate stuff. That's my version of what Apache Spark actually does. One of the cool things that I found in Apache Spark is that it offers you a lot of machine learning algorithms. For example, there are binary classifiers. So it can tell you this email is a spam email or not. There's a linear regression algorithm in there, so it can predict what your car will sell for, given a number of properties. And loads and loads more of that kind of stuff. And the cool thing about Apache Spark also is that it runs everything in memory, so it's very fast. You can do real-time computations. Well, as real-time as a computer gets. So how does it work? There's a number of ways in which you can build Spark programs, actually run them, basically. And it all comes down to this sort of structure. There's a Spark master in your network. This is the place where you submit your job, your Spark job. And the Spark job, I will get to that in a minute, is a small Scala or Java program, or Python, for anyone that likes that. Anyone doing Python? A few, okay. You can run Python on Spark, so that's cool if you like that. And once you've submitted your job to the Spark master, it will split up your data into partitions and try to distribute it over a number of slaves, which makes it a lot faster. Because if you have a terabyte of data and will go to one computer, it will take some time. If you split it up into 100 computers, it will get faster. So this is how Spark works. And the idea is that you write the program, and that's all you have to care about. At least after you've installed Spark on your computer or on your data center and configured it. Spark programs aren't, in my opinion, not very complex. What you need to do is you need to, in your application, you need to create a new Spark configuration object, set a master, and set the app name. And the reason why I'm setting the app name is because otherwise, if you have a large Spark cluster that runs multiple jobs, there's no way you're going to find your job if you don't set a name. So one of those little tips that I give people, always set a name for your application. Otherwise, you will get lost. Okay, if you're on your development machine, it doesn't matter much, but it's a good practice and I'd like to stick to it. And the last thing you need to do is you create a Spark context. I learned, I'm normally a C# guy, so this is kind of okay. Scala developers like to write less code. So I don't know if this is too long for your taste, but I managed to at least compress this one as C, Spark context. I heard someone say, write once, read never. That's good. That's what I learned from Scala. I don't know if it's a good idea or not. Probably not, but yeah. So once you have the Spark context, you can start to run code against your Spark cluster. The Spark context will take care of everything. The partitioning, sending data off to a slave, getting data back, everything. What you can do, for example, is say, okay, Spark context, read a text file, some file.csv. And it comes from the local hard drive, so this is kind of interesting. We're running in a distributed environment, and I'm going to the local hard drive. Don't do this on production, it doesn't work. What you need in production is HDFS or a Cassandra server or a SQL server, or at least something that is shared amongst the servers that are running Spark. The next thing I can do is say, okay, I get lines out of the text file, and I can split them on the comma-separated file. So. And after that, I can convert it to a set of some data case classes. The above part, the first 3 lines of code, do nothing if you don't do the count. And that's because you tell Spark to basically build a program, the map part of your program, and then once you start a count, there's a reduce operation, then it will send the data off to the slaves and run the computation and come back with a result. Before that, it doesn't know how to do that. Once you ask for a count, it will know, oh, okay, I have to partition the data. On every server, I run a count, and then I sum over them, and then I give the result back. That's the idea. So that's Spark, very short. And you can do a lot more stuff. Spark has support for streams, it has machine learning support, it has graph support, so you can run graph computations, shorted paths analysis, and all that sort of stuff. Very cool. If you haven't tried, go try it out, and leave a tweet if you like, if you have any questions or want to try something out. Okay, so now that you've seen your first Spark program, I'm going very fast over here. By no means an expert at the end, I think. Let's go back to our recommendation system. So what are recommendations, actually? If you look at items and users and how they relate to each other, then there's a matrix that I can build, and I can say, okay, I've watched the movie Avengers, and I really, really liked it. I gave it a rating of 5. So I really like that movie. I do that for a number of other movies. So horizontally, the columns in the matrix, those are the movies that I like. And horizontally, the rows, those are the users that liked the movie. So far with me? Makes sense, right? Okay. Now here comes the trick. Apache Spark implements the alternating least squares algorithm. And what it basically tries to do is build a formula that does this. I have those users and items. I've given a rating. But why did I give that rating to the movie? Well, that happens because I did like 5 properties of that movie. I liked Avengers because it's an action movie. I liked Avengers because someone played in it. I liked the Avengers movies because it's about superheroes. Those are properties that you can choose. And I'm going to say choose because actually it doesn't have to be those properties that I just mentioned. I'm only going to tell the computer I would like 5 properties. Thank you very much. There are 5 properties that describe the movie, and there are 5 properties that describe the user. And those are the same properties. So if you multiply one of those properties from the user with an item, I should get back the rating. So far, so good? Still makes sense, right? It's not very complicated. There's, bear with me, I'm really, so this is actually the formula. But you have to agree with me. How am I going to find those 5 properties in the first place? I just stick them out of my thumb. I say 5 properties. Okay, random guess. I don't know if that's going to be correct, right? It could be 10. I don't know. And at the same time, if you look at this formula, there are 2 terms in the formula that are unknown because I randomly choose 5 properties. So there's no way you're going to find the most optimal solution for this. So we're going to do another trick. You saw these vectors, these matrices. And what I've done, I've chosen random numbers for one of them. I was puzzled. I was looking at the code in Apache Spark, and the developer said in the comment, choose random numbers for one of them. Why would you do that? That's simply because I cannot solve them both at once. The values for the properties of a user and the values for properties of a movie. You cannot do that at the same time. It's a non-convex problem for the mathematicians among us, and it means there's no optimal solution if you try to solve both of these parts of the formula. So what do? Well, the scientists came up with a solution. What they did is, I'm going to take the U matrix for the user, I'm going to pick random numbers for every cell in the matrix. And then I'm going to try and approach the rating matrix that I showed earlier, the most left part, by modifying the values in the other matrix, in the item matrix. And you can do that. There's a so-called cost function that you can use, and you can run a formula, least squares is the formula, and that's an approximation. What it tries to do is tries to minimize the error between the predicted rating and the actual rating. And for those of you that have done machine learning before, linear regression is very much that. It tries to take a real value, that rating of 5, and try to approach that by modifying the formula so that the computer can predict that very same value. It won't reach it. And especially in a recommender system, it won't reach it. And it happens because this formula has 2 unknown parts, and one of them is random. And the other one I try to optimize. The computer can't solve this. So like I said at the start of the presentation, it's the art of approximation. It will get there somehow, a little bit. We'll try to approach what it really is. But it cannot do that because we don't know what you like. Netflix is incapable of guessing that you like action movies. It doesn't know because it never tracked that sort of information. So what they try to do is model that in these matrices. That's what we're trying to do. So we've picked random numbers for the first one, and we solved the second. And what we do is, it's alternating least squares. So we're going to do the same trick. We pick the solved matrix for the I component in this formula, and we're going to try again to optimize the values in the user matrix. And we're going to alternate that a number of times. 10 times, approximately, 15 times. You don't know yet, because it's a problem that the computer cannot solve for 100%. So-called NP-hard problems are very difficult for the computer. It might never reach an optimal state. So, yeah, recommendations, it's more difficult than you think at first. If I start out with a matrix and rating matrix and I tell you there's a reason why you get this rating, then you're all, oh, okay, I was like that too. Okay. And then I jumped into this formula, and I was thinking, how are they doing this? I don't get it anymore. Cost functions, partial derivatives. If you're into that sort of thing, there's a massive online course on Coursera on machine learning. I suggest you watch that one time and then stop. Never look back. Because why do we need to know all that? All we need to know is that the computer somehow tries to find out why you like a movie, or why you like a song, or why you like a certain article on a weblog. That's the thought that you need to keep in mind. Okay, there has to be a sort of approximation. Why am I liking this? So all you need to know is this. I'm asking Spark, hello there Spark, I would like the user rating table. I would like to get rating objects out of it that have a user ID, the user that gives the rating, an item ID, the item that I like, and the rating I gave. And then I'm going to say alternating least squares dot train. Hello, the alternating least squares. I would like you to try to solve the formula. So it all boils down to one line. And there's still a lot of magic in this, don't get me wrong, because I still haven't showed you whether this is correct or not. These settings could be well wrong. Remember, it's random. So yeah, I don't know. So what I've done, I've picked 3 numbers that are coming from the documentation. Rank 10, those are the 10 properties I'm trying to approximate. Iterations, how many times am I going to do the alternating procedure? And last, lambda is the learning rate, that has to do with the linear regression formula it is trying to use to optimize the predicted rating versus the actual rating. And all you need to know about the last one, the lambda, is that it needs to be very small. 0, 0, 1 is about right. I'll get back. So what you will get out of this is a matrix factorization model. That's what it's called. And a matrix factorization model, you can ask for recommendations later on. So now that I have a trained model, I can use it in my applications. Of course, you could just run the Apache Spark job and let it generate recommendations for all the users and store that in the database, and then use that in my application. You could do that. But I thought of a better way. At least this morning I talked to someone from Lightband, and he showed me another way which is even more cool. So maybe I will use that for Berlin, but not today. What I did is I used Akka to provide a way to talk to my trained model of my recommendation system. So the application looks like this. There's a recommender system in my application, because that is what it's about. And it has a model. So these are all actors, except for the most left part, the HTTP part. And what you can do is you can send a message over HTTP to my service. Hi, I would like recommendations. And that will get you back recommendations. And the other thing you can do is you can send in the message to train a model. And I've made it in such a way that if you are training a model, which can take a long time, machine learning algorithms run for a long time, while querying them is very fast. So that's a good thing to keep in mind over here. So querying them very fast, and I need to scale out for the number of users that are using my REST service. And on the back end, if I have a large amount of data that I use to generate recommendations, to train my model, basically, then that needs to scale out based on the number of records I have in the database. So there's another tip. Think about where you want to scale and how you want to scale. I'm not going to bore you with the bits about the HTTP routes and all that sort of stuff. The code is on GitHub, so you can try it out over there. I'm just going to walk you through some of the general things that I've done. One of the things that I've done is the recommender system has an optional model. And I chose this option because I think that if the model is not trained, the service should just generate no recommendation. It shouldn't crash. Never. There's no use in a crashing service. Instead, give me a slight hint like, yeah, sorry, I don't have recommendations for you. Doesn't work today, sorry. What will happen is once I start to send it the message train, it will start to train the model. And to train the model, it will spin up the recommender system trainer actor, and that actor will talk to Spark and call the ls.train method. And so what I've actually done, if I have distributed my job to the background, goodbye, I don't want to know, get back to me when you're done. And the rest of the REST service will keep on running. So in an initial case, the model is empty, there's none. So the user will get empty recommendations. But once there is a model, it will keep on serving that model until I am done training another model. So you could, theoretically, continuously train your recommender system based on changes that happen by the users. But one of the other things that happens in machine learning is that, okay, I've made this slightly simpler to work with Spark, but the model will be becoming much worse, actually. It starts out bad, 80%. That's what I'm aiming for. But gradually, as you start watching movies and listening to music, I will learn new patterns because I recommended some weird band from Germany or something to you, and you really like that. And based on that, I will discover that you like German music. I don't know if that happens ever, but it could be. So the model gets worse. So I provide a specialized endpoint to explicitly start to train the model again and replace my old model when I'm done. So how do I generate the recommendations? Well, once I have the model, I can ask it for recommendations. And I've done a very functional trick. I say model.flatmap, and flatmap on an optional will not fire if it's a none. If it's a sum, it will fire and my code will continue. Hey, no exception handling. I wish we had that in C#. Then, when my flatmap runs, my model will recommend products, and I will generate products for my user that I specified and the number of products I want. And it's very generic. What it will do, it will, from the matrix that I've generated, with the predictions for items that I didn't know yet, it will pick the top 10 most relevant items based on the calculated rating. And that's what you get back. So once I get that back, I will say, okay, convert it to my own internal representation, and if everything else fails, give me an empty list. That's all it does. And once I have the recommendations, I will get them back over the REST service. In this case, Akka HTTP. Does it sound complicated to use? I see one question. Just thinking, okay. Can happen. It happens to me all the time. That's why I come up with these weird ideas. But, okay, so far, I've asked my computer, based on ratings that I have in my database, to generate a set of random numbers for a set of recommendations. This could go wrong, very wrong. I mean, how on earth is that going to work? Well, there's a very scientific approach to test this sort of thing, and that is, what you do is every time the user asks for recommendations, store them somewhere in a database. The fact that you've generated recommendations for the user. And it's as simple as this. User ID, item ID, and a score. And when you've generated, if you like. It doesn't really, it's not necessary to have that, but could be useful. The next thing you do is you implement a small piece of code in your application that records that when someone selects an item in a database, you record somewhere in the database that that item is selected. And the third step is, okay, I've generated a list of recommended items for the user, and he has clicked a few items. I'm assuming here that the items he selected in the front end are the items he finds interesting. Mind you, this is not very scientific, but it works. We've tried this on production. We call it stealth testing. And we use this very often for all sorts of processes. And this way we can find out if the recommendations are remotely correct. So the first time, your recommendations will be wrong. I'm just saying. The first attempt you take at this will be very, 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 very wrong. Don't worry if you do continuous delivery. I hope you do. Anybody doing continuous deployment on production? I hope so. There's one hand. Uh-oh. There's another hand. Serious? Nobody doing this yet? I can really recommend this. For if you're building this, the first time it will be wrong. So if you want to fix this, if you discover that your recommendations are wrong, I suggest that you implement some form of continuous deployment so that you can tweak those parameters I talked about earlier, the iterations, the rank, and the lambda, so that you can quickly improve the recommendations. This is how it works. This is what we do at KnowNow. We take this algorithm, we deploy it on production, we run these 3 steps, and we discover, uh-oh, it's wrong. Okay, I'm going to tweak it and try again. And we can do that every 5 minutes or so, because our build is slow. But yeah, you gotta go somewhere. So back to the number crunching. So this is how it works. What we do is we say items that are really interesting. Those are the items that the user clicked. The other items that the user didn't click in the database are not interesting. Also an assumption, because I don't know. But, well, you gotta start somewhere. You have to do something to solve this problem. Next, I'm going to look at the predicted items. Items that I've predicted in the front end, that I've shown to the user are interesting. At least I think they are. The other items I didn't show are potentially not interesting. Again, this is an assumption. I could be wrong, because item number 10 to 20, 11 to 20 could still be interesting, but I've never shown them, so you never know what's going to happen. And from these numbers in the confusion matrix, if you're interested in more of this, I suggest you Google for confusion matrix. It's one of the validation techniques in machine learning to validate recommendation systems. And from this matrix, you can calculate the precision. That's the amount of items that I predicted that were also correct. So I calculate the items that I've recommended in the front end, and that were interested, and I add to that the number of items that were truly not interesting, and divide that by the total number of items that I have. And that will get me a precision. How many items of what I predicted were correct? So that means that if you recommend 10 movies and say out of those 10 movies, 8 were good, were the ones that I liked, and I'm doing pretty good, 80%. The other metric is how many items from the set of items that I have in a database. For example, if I recommend you 10 movies out of 35,000, then I could say recall is a little bit low. But from those 35,000, only 1,000 could be interesting. I don't know yet. But using the confusion matrix, you can calculate this. There is an interesting relationship between the two, and that's the reason why I'm showing them. Precision, I'd say, is pretty important. However, if I'm trying to sell cool shoes, then it could be more important to have all the shoes available in the front end. As many shoes from my collection as possible, because that's increasing the chance that you're actually going to buy shoes. It's a sort of thought. So recall could sometimes be more important than precision. And there's an interesting problem with these two measurements. If I show just one item to the user, I have a 50% chance that that's correct. So potentially the precision in that case of a single item could be 0, which is pretty bad. But it could also be 100%. Getting lucky. So what do? Well, the solution is showing more items, for example 5. But then the precision lowers. but the recall increases because, yeah, there's a larger amount of items that I pull from the database and show to the user. That's the recall. So you cannot maximize precision and recall, not at the same time. So you have to make a choice. And here's where it gets interesting and where I think it gets very cool if you talk about recommender systems, and why I think Netflix is actually doing a pretty good job, despite the fact that some people maybe dislike recommendations. Is there anyone in the room that has ever had only good movies from the recommendations from Netflix? You know the one on the homepage? Never, huh? Another question. Did you ever click on a movie that you didn't like at first sight on Netflix? Maybe on a boring Saturday night, raining. Yeah. That's because they choose a sweet spot, somewhere halfway the graph. It's weird, huh? On the one hand, if you try to approach 100% in precision, you're going to show the movies that the user expects to see. And those are probably the movies that he already saw. Because I can approximate those the best with this algorithm. On the other hand, if I don't do that and I maximize recall, I get movies you've never seen, and you probably go like, forget it, Netflix, I'm going to the next neighbor. I don't know, Hulu or something in the States. Do you have any alternatives to Netflix? Amazon Prime, for example, because they choose a different setting. I mean, that's how it goes. So if you're going to add recommendations to your system, think about this, and sometimes deliberately choose a value for precision that's lower than the 80%. It promotes discovery of new content that the user hasn't seen before, while at the same time maintaining that feeling that it's connected to you, that the user has an idea of, oh, I know this, yeah, oh, the other movie is also cool. So in this case, in this specific appliance of machine learning, it's best to spend a little bit of time tuning this. And the sweet spot is somewhere in there. Sometimes it's better to use a higher recall, sometimes it's better to use a higher precision. So I thought about it, and I got a lot of questions about this during I do a course on machine learning for our own company, and a lot of people that follow the course talk to me and say, well, yeah, I can't write unit tests for this. No, you can't. Well, you could do a little bit. Maybe a mock for your recommender system and try to see if the HTTP connection is okay. Could do that. But obviously, for machine learning solutions, there is no way you're going to write a single unit test that's always right. It will probably flip during the build, sometimes red, sometimes green, because, yeah, it's an NP hard problem. You can't get there. So another tip I'd like to give you, if you're going to build a machine learning solution like this, spend a little bit more money on monitoring the system. Spend some time and money on these steps. This is where your investment should be for a machine learning solution. Get real feedback from the users. Ask them what they like and didn't like. Because machine learning is very, very cool. I really like it. I suggest you use it for everything that you build. I don't mind, but please be aware that a human is always the last one to check if it's right or not. Because machines are like this. They don't see left and right. They don't have a gut feeling. They don't have emotions. They don't know. They just know the mathematical formula for recommendations. And they got it wrong too. I mean, how are you going to trust that? So, if you're trying this out, I've got the code up on GitHub. It's open source, you can download it. You can leave issues if you like, if you run into any trouble. The README file is very short at the moment. Download this, load a bunch of data, and that's it. But I will extend that, and yeah, if you have any questions, please shout out. Yes? The question is, how do I measure false positives? Well, false negatives. Those are very hard to predict. Those are items that I didn't recommend, but are in the database. So the question for people that didn't hear, how do I measure false negatives? Well, the thing is, this is all based around a bunch of assumptions. So sometimes the user clicks on an item that I haven't recommended as a false negative. Yeah. So the whole measurement thing is based around a totally disconnected system. There's no relationship between the click stream, so to speak, the items the user click, and the recommender system. We haven't done that in KnowNow or anywhere else because it would be kind of hard to do that. Otherwise, you wouldn't be able to extract the false negatives. So, does that answer your question? Cool. More questions? Yeah.
Dimension metrics, right? So you show the users plus the items, right?
Yeah.
So if the item size and the user size both are big, what is the best approach for it? Is it the precision or the recall?
That's a good question. I have a two-dimensional matrix that I'm trying to solve.
Yeah.
And I assume you're talking about the confusion matrix.
Yeah, confusion matrix. But
Yeah.
the sample size is big for both the sides.
Mm-hmm.
Then, what's the best approach? Precision or recall?
That's a good question. Which approach is the best? There isn't. It totally depends on what you're doing. You can use a recommender system for recommending movies. And like I said, Netflix approaches this in a way that they say, okay, we're going for the middle of the chart that I showed. We're going for a little bit precision and a little bit recall, about 50-50. But if you have to recommend items that the user already knows, I can't come up with a use case for that right now, but if you want to use that, then precision is more important. But if you're a web shop and you're trying to show as many items in your catalog as you want, as is possible, then recall is more important. There's one thing to keep in mind: you can't maximize both. You cannot do that. So, sorry, there's no best approach. Any other questions? Yeah. Yeah.
So in order to do that, sometimes people, what they do, they categorize or classify the items, right? And then they go with the US precisions, and then they try to recommend on the precisions. And by the categorizations, it can it also considers the recall, so that they don't need to consider the other stuff. They can come into a particular categories, and then they.
Yeah. So that's a good one to mention. I've simplified this scenario to a number of items, but you can imagine 35,000 titles, 100+ million users is getting pretty big. And I'm not sure how Netflix manages the size, but if you're an online retailer, like you said, and you have trouble getting the data into a manageable size, you could always run individual training runs per category on your web shop. Again, I'm not sure what the results will be like. I don't know. It could be all wrong, but you have to try it out. This is pure experimentation. That's why I mentioned continuous deployment. If you can deploy these solutions quickly, you can experiment and see what the users like and don't like. Yeah, another question.
How crazy would it be to allow a user to, like I know some movie people, they just watch movies constantly, and then I know some people that they literally just want to watch the same 10 movies over and over again.
Uh-huh.
So how complicated would it be to allow the user to kind of move that precision versus recall scale?
Ah, that's a good one, yeah.
I want more recall, or I want more precision.
The question is, would it be possible to let the user choose whether he would like precision versus recall as the most important measure? For example, there's one solution. There's one problem. When you train the system and you start to gather feedback, then you will have to fiddle with the rank, the iterations, and the lambda. and that those 3 measures are for everyone. It is not for a single user. That's going to be a big problem. Otherwise, what you would do is train a single model for every user. I don't know how crazy that is. Could be worth a try.
Or buckets at least.
Yeah, that could be.
Like 3 buckets and you ran it for everyone. Now that would be super expensive, but if your model was, I want to keep all my users, I'm going to give them 3 buckets to choose from.
Yeah, you could do that. Yeah, you could train 3 models that would at one for precision, one for the middle situation, and one for the recall. You could do that. Again, it all depends on the data size you have. If you have a few terabyte, I think it would be manageable. If you have something like Netflix, I don't know. Yeah, and it's good to mention this is a very simplified picture of the situation in Netflix. Netflix these days uses 6 models combined, so I don't know. It's kind of on a different ballpark. Any more questions? I don't know how to.
So does the precision and the recall return different sets, or is there an intersection in between them, or are they different results from each precision and recall?
That's a good question. Is the measurement of precision and recall between each training run the same? No, they fluctuate a little bit. So sometimes it could happen that you have the same settings but run the training session 2 times and you get a different error rate. That's because it's an NP hard situation and the computer is choosing random numbers. So that's why monitoring this sort of thing is important. You have to follow the precision and recall over time. And if it suddenly drops or suddenly is higher than what you'd expect, then you have to do something. Then you have to go and find out what is going on. Do I need to change the rank? Do I need to change the iterations? Do I need to things like that? So, yeah. Does that answer your question? Yeah. Okay, cool. I think I have time for one more question. No? Cool. Thanks. Oh, yeah. You get a score for every recommendation.
So you could increase the recall and then show the movers in the highest score first. So
Yeah, that's how it works. So you calculate a predicted rating for every item, and it sorts it from highest to lowest, and the top 10 is the one you are giving back. But still, the top 10 could be wrong.
But if they're in order, then the precision is less.
It could still happen that you predicted a rating of 5 for an item, but it's actually a 1. It could happen, and then it's not working. So, yeah. That's why I chose this validation method over some other method where you look at the score. Yeah, just what it happens to be. Cool. Thanks for your time.